Welcome to this short series on the fundamentals of control engineering. Today, we start by reviewing the concept of dynamical systems, which is of fundamental importance in this field. A dynamical system is an abstract way of representing, basically any physical system of interest. Examples may range from robots to electrical circuits, motors, fluids, population dynamics, and so on. Any dynamical system will be represented by a set of variables which define its state. Such variables summarize the past history of the system and provide all the information we need to forecast its future evolution. We denote these variables by x. And since in all the examples we will consider x to be a function of time, let me write down explicitly x of t. We can represent our system as a block in what is called a block diagram. So let me draw a nice box around our system. Their evolution will depend on other quantities which we may or may not be allowed to control, and which are the inputs to our system. We can represent this by adding an arrow entering our block, and by denoting inputs as u of t. Moreover, in many cases, we may not be able to measure the state of the system directly. We may only have partial access to it, or only know some function of it. In general, we will only be allowed to inspect the output variables of our system, which we denote by y of t. For a physically meaningful system, we also typically request some additional conditions. Two very important ones are causality, which means that future inputs cannot influence the current state of the system. This is a fundamental property of most physical processes. There may be some specific cases where you could apply some of the theory behind dynamical systems to analyze known causal examples, for instance when applying filtering to pre-recorded signals. However, from a conceptual point of view, we will almost invariably require that our systems are causal. Another important property is separation. Any point of the trajectory can serve as an initial point for our investigation. Following the trajectory of the system from such point must provide the same results. To make an example, imagine you are driving from Rome to Milan and that your state variables, for any reason, are the travel distance and the fuel you have consumed. It is a pretty long trip, but if you stop along the way to rest, say in Florence, and continue your trip the next day, you will expect that the total travel distance and fuel consumption from Rome to Milan are the same as the sum of your partial distance and consumption measured in Florence, which would be your new initial state, plus the distance from Florence to Milan and the fuel burned to cover it. We'll come back to these properties in a moment. In the simplest case, our system will admit an explicit representation, which looks like this. First, we have a so-called state transition function. This function expresses the state x at time t as a function of the current time, the initial time, the initial point of the trajectory, x0, and of the inputs fed to the system in the interval t0 up to t. As we said, the trajectory of the system is completely known once its initial state x0 is given, along with the values of the input variables. Second, we have the output function. This function represents the relationship between the outputs y of t, the state x at time t, and the input u at the same time t. This relation might also explicitly depend on the time. Note that y only depends on x and u at the same time. All of the history or dynamics of our system is contained in the x variables, of which y is just an alternative or maybe reduced representation. As a first very simple example, think of the motion of a material point. Let me draw a particle of mass m subject to an external force that we call F. For simplicity, assume that the force F is constant and that the particle can only move in one dimension. The motion of our particle can be described by the well-known Newton's law. We can also write it as F, the force, equals m, the mass of the particle, times the second derivative in time of the position of the particle, which we denote by x double dot. The dot notation represents derivative with respect to time, and it's a pretty standard notation in control engineering. You may probably have seen the solution to this problem in undergrad physics, where the position of the particle, which we denote by xp, function of time, is given by its initial position xp0 plus its initial velocity v p0 multiplied times the elapsed time, t minus the initial time t naught, plus 1/2 of the force over mass, which is the acceleration of the particle, multiplied times the square of the elapsed time. And for the velocity, we have that v of p as a function of time is given by the initial velocity of the particle plus the acceleration of the particle, so again f over m, times the elapsed time. Note that we cannot describe the evolution of the position xp without also knowing the initial velocity of the particle. Hence, xp is not enough to serve as the state of our system. We can, on the other hand, describe the evolution of the position xp and velocity vp once their initial values are prescribed. So this will be the states of our system, and we can write that our x of t, using the same notation as before, is the stack of xp and vp. In this very simple case, we have an explicit representation of the system, like the one we have seen before, given by the laws written here. This takes the form of a mathematical law which describes the relation between the states of the system, xp and vp, and both their initial values, the initial and current time instance, and the system's inputs, which in this case is just force f. Finally, we may only be able to measure the position of the particle xp, for example, but not its velocity. And this would give us an output relation, which has the form y of t simply equals xp of t. As we have seen, for a physical system, we will usually require some properties to hold. The first of these is consistency. According to this property, the state transition function evaluated at the initial point of the trajectory must return the initial point itself. We can write this as phi of t naught again, x naught, and u applied at t naught is just x naught. And in most cases, we can also neglect the inputs at time t naught. This is true because of a strong version of causality, which we'll discuss later. And the second property is indeed causality. As we said, this property tells us that future inputs cannot influence the current state of the system. This can be expressed as follows. Imagine we have two functions u of t and v of t, which are equal up to some time capital T. Then, if we consider the trajectories generated by these two inputs, which can be written as then these trajectories must be equal for any t in the interval t naught capital T. Finally, we have separation. Let us consider a point x1 given by the function phi at time t1, starting from some initial point x0. Then a generic point x of t for t larger than t1, expressed by phi of t starting from the same initial point, so along the same trajectory, can be written as follows. This property tells us something about the composition of the state transition function with itself. In fact, this can also be written as phi again. And here you see that phi is applied to the output of phi from t0 to t1. We can also classify our dynamical systems. A system will be said to be autonomous if it has no input. It will be said to be strictly proper if the output y does not depend on u. It is static or algebraic if it has, on the other hand, no internal state, so if y only depends on u. And finally, it is said to be stationary or time invariant if it bears no explicit dependence on time t. In this case, the system will be invariant under translations of the inputs. And actually, let me write this explicitly by denoting u as u of t minus t naught. In general, though, explicit representations of dynamical systems are rarely available. Most physical systems are described by implicit representations, often in the form of differential equations. Think of the point mass example made earlier. The explicit law we have seen only holds for a constant f, while a much more powerful representation is just Newton's law itself. In this case, the system will take the form of equations which relate the state variables x and possibly their derivatives to the system's inputs and outputs. We can write these equations as Note that we can always stop at the first order of derivation by defining additional state variables, just as we have done before with position and velocity. If we can at least separate the derivatives and the outputs from the rest, then we obtain the most common representation of a general dynamical system. This is a so-called input state output representation of our system, where the derivative of the state variables and the output variables are related through some generic functions to the time, the state, and the inputs at the considered time instant. Input-output representations also exist, and we will discuss them later. Before closing this video, a final note. So far we have seen continuous time systems. However, systems can also come in discrete time form. This is very common, for example, when we deal with digital or sample systems, or in population dynamics where we look at consecutive generations. In this case, we typically label the time instance with integers. For example, if we have a sampling time, which we call Ts, we might consider T as the product of an integer k times the sampling time Ts, where k is again some integer number. We can write then that x at step k plus 1 is some function of the previous, actually of k itself, of the previous state, x of k, and of the input, u of k. And similarly, y of k will be some other function of k, x of k, and u of k.